Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones. Hi, it's Surface Mount Soldering Time Part 3 in the hand soldering tutorial, and today we're going to do surface mount technology. We've looked at the tools in the first part, through-hole components in the second part, and surface mount. A lot of people think it's really hard, but it's not. It's an absolute piece of cake. Use the basic techniques you did last time, a few more little tricks, and you can solder really first-class stuff with not much experience at all and some very basic tools. Let's take a look at it. Let's start out by looking at some basic surface mount components here. Up here is your standard quarter watt through-hole resistor everyone's familiar with. Now, this is a 1206 size surface mount resistor. This is a 0805 surface mount ceramic capacitor. This is the same size 0805 surface mount resistor. This is an 0603 surface mount resistor, and this is an 0402 surface mount resistor. They do come even smaller than this, tiny ones that are used in really ultra miniature mobile phones and things like that. Now, the 1206, but these are the basic standard sizes that you'll deal with in terms of your basic resistors and capacitors, your basic passive components. Now, the 1206 up here is an absolute monster. Stevie Wonder could solder this thing. It is so damn easy. Let me tell you now, 0805's really very easy to do as well. Once you get down to 0603, it gets a little bit more touchy, but I can easily do 0603 by eye. I don't need any magnification at all, and you should, most people will generally be able to solder an 0603. So if you're designing your boards, especially for hand soldering and even for surface mount soldering as well, try and avoid the 0402s. Now, I can do those by eye but I much prefer to use to solder under either a ×4 or a ×6 magnification there, just so that I can, keep a much tighter control of how much solder I feed on the joint, and just inspect the joint at the same time as I'm doing the components. So if you're designing your own boards, I would stick to 0603 and up, because once you get down to 0402, if you're actually getting PCBs hand assembled prototype, they'll charge you a lot more for 0402s, because they will generally solder them under the microscope as well. Whereas if you're getting some prototype board hand soldered, 0603 and up, they can do by eye. So really, just put some thought into which components you use. Don't just jump right in and use 0402s. Now, for today's example, I'm just going to solder an 0603 part. And if you're talking about automated pick and place assembly of your boards, when you're designing your boards, put a bit of thought into it. Once again, if you use 0402s, you might be in trouble, because there are basically two classes or two technologies of surface mount pick and place machines. Cheaper and older designs can only do 0603 and above components to at least a reliable level. They might be able to do 0402, but their yield isn't as good. So if you're getting your board assembled by a manufacturer, they may actually charge you more to use place 0402 components, because they might have to use one of their more advanced machines. The yield might not be as good and things like that. So just put a bit of thought into it. It might cost you a bit more to go down there. So don't make it an arbitrary choice to go to 0402s. Make sure you have a reason to do it. Now, here's our 0603 resistor that we're going to solder onto this board, and as you can see, it's going to be fairly easy because the pads are actually quite large in comparison to the component. They do actually extend out further, and this is great for hand soldering. Now, if you're laying out your own boards like this, the IPC footprints, the international standard footprints, they actually come in three basic sizes: what's called normal, least, and most pad size. Now, I'd recommend using the normal or the most pad size. Most means it's got the largest pad size, and they're the ones that are suitable for getting your iron in there to make contact with both the pad and the end cap on the component at the same time. And that's important. If you use the least pad size or even a custom pad size, some pads are really no bigger than the tiny little end cap on that resistor, and really there's no way that you can actually get your iron in there to make contact with both. You've got to put solder on the end and bring it over and maybe get under there and actually thermally transfer the heat through the cap onto the pad, and it gets really nasty. So just if you're actually designing your boards and you think that they may be reworked hand soldered, or prototypes are going to be assembled hand soldered, if you can afford the room on your board, if it's not a super compact layout, highly recommend you go for a larger pad size so that you can get that thermal contact. Now, we're going to use a method today called the Tack and Reflow method for doing these components, and as you'll see later, it applies to other parts as well. It basically means that we're going to tack the component down first and then solder the other side. And if I'm doing a whole array of components like this, I will do it in like a batch process. I'll do a single resistor here, but if I'm doing a whole bunch like this, I would go through and apply solder to, I'll do one step, apply solder to all these pads first, and then I will go and place my resistor and then tack it down, tack the resistor down onto each pad as a second batch step, and then I'll flip my board around to the other side, or if you're left-handed, if you're ambidextrous, you can solder with both hands. You can then you go through and you complete the joint on the other side. So that's a batch process, but I only show a single resistor today. Now we aren't going to need any flux for this because there's flux built into this into the core of the solder here. So let's actually just apply a small amount of solder, just a tiny amount, onto that pad there, and that will allow us to tack down this component. So if we grab it with the tweezers like this and we get in there, it's important to make sure the component doesn't flip up like that. It's hard on the camera, I can't get my tweezers down vertical, but if I get my resistor in there and I just reflow it like that, and really we've soldered one side of the resistor there. Beautiful. And we just flip our board around like that, and we go in, grab our iron again, and get in there with our, once again I'm using very fine solder, 0.46 millimeter solder, tiny stuff. I highly recommend you get that size or smaller for this kind of surface mount work. Forget using 0.7 or 1 millimeter solder. Really, you're going to do a horrible job. You're going to feed too much solder in there. It'll just look very amateurish. It'll be horrible. Trust me. Spend good money, get good quality fine solder, and we go in there and there we go. We just tack down the solder the other side of that component, and bingo, we've soldered an 0603 surface mount resistor. And it's the same for a capacitor, it's the same for 0402 size, 1206, 0805, whatever. Or it's also very similar for other components like a SOT23 and things like that. So it's really quite easy to solder these components. Give it a try. Piece of cake. And after you've soldered small parts like this, you just want to get in there with your jeweler's loupe, one of these, or your inspection microscope or something like that, and just check that that the resistors are soldered nicely. And once again, as with any solder joint, should be nice, shiny, very nice, shiny and smooth finish, and it should have a very nice fillet there on either side of the resistor. That one there's slightly crooked, a little bit off center, but generally that's not a bad job at all. Okay, now let's try and solder this very typical 8-pin SO package IC here. Very easy to do by hand, even if you haven't done SMD soldering at all, because the pin pitch is reasonably large. It's half that of a standard dip-based IC. Instead of 0.1 inch, it's 0.05 inch or 1.27 millimeter pin pitch in the metric scale, and that's actually quite large, and you can get in and with your soldering iron and actually solder, very fine solder, and solder each individual pin. This is one way to do it. There are other methods, as we'll see, which are better used on smaller pin pitch parts, but these SO packages, I like to just solder each individual pin by hand with my iron. And how we're going to do this is we're going to use the Reflow, the Tack and Reflow soldering method. So I'm going to put my iron on there, and I'm going to just tin that little pad there. It needs to be sort of a small size lump of solder on there. You don't want to tin it completely flat, because then there won't be enough solder on there to actually tack down your component. And the whole idea is that we want to bring in our component. This is where our tweezers can come in handy, and we want to actually tack that pin down on there like so, and that holds our chip in place, and we can solder the other pins. Flip that around to the other side, and we just want to solder the diagonally opposite pin. So get your iron in there, chisel tip, which heats up the pin and the pad at the same time, and just apply a small amount of solder in there, and it will will just flow onto both the pin and the pad, and you should get a very nice fillet in there. It's hard to get. I can't really zoom in much more than that, but you should get a really nice shiny finish as well, with no burrs and no things sticking out, no shorts to other pins. Because we've got the solder mask on these boards, solder mask is vital for surface mount soldering work. This is the red material that you see on the board, but it also comes in other colours. You've seen green, and there's blue, and there's black, and there's yellow, and there's white, and there's all sorts of colours that you can get. But solder mask is vital, because the solder mask will actually go between each individual pad like that, and it will help prevent, unless you're really bad at soldering, prevent shorts between the individual pins. And that's really important, as we'll see on the much finer pin pitch components. But as you'll see, I can sort of, solder all I want. On try and attempt to put solder onto this solder mask, it'll blacken, but it will never ever take. And by having the solder mask in between the individual pins like that on a board, it just helps keep the solder out, because it's not sticky at all. The solder will just naturally want to flow into the individual pins and not get stuck between the pins. Place our iron there once again for a second or two, just like through hole work, and apply the solder not to the iron itself, although it's hard when you're at this sort of pin pitch, but apply it to the pin or the pad if you can get access to the pad, and it will flow onto the joint like that. Bingo, we have one side nicely soldered. And with practice, you can do this incredibly quickly, just as quick or even quicker than through-hole work. And then we'll get in there with our jeweler's loop, and we'll just have a look to make sure the solder joints are good, and we can actually see that there's no shorts in there. And as you can see, I got a little bit of solder splash onto this pad here. You've got to be careful not to do that. It's because I'm working under the camera here, and I had to use a shallower angle, soldering iron at a shallower angle than I normally would. But as you can see, those joints have turned out quite nice, because I've used 0.46mm solder. I've used a nice chisel point soldering iron, which allowed me to heat the pin and the pad at the same time. I was able to get in there nice and quick, and that is a nicely soldered surface mount chip, and it really is easy. Give it a go. Now let's try and solder a much smaller pin pitch of 0.65mm pitch device. Let's see how we go. And remember, it's got the solder mask in between the pads. Let's start out by tinning one of the pads, shall we? There we go. And this will allow us to reflow, what's called reflow our part into position, because this is the reflow soldering process, because there's already solder on the pad itself, and all we do is heat it up, be it with a soldering iron or with an infrared reflow oven or a toaster oven, as you may be familiar with. A lot of people use those, and this is how they mass assemble boards after they've pick and place them using the reflow process. We've done a very similar thing here, or an identical thing, but we've just used a hand soldering iron. And with this pin pitch, I'm not actually using any visual magnification at all. I'm viewing this on the camcorder screen here, but I can solder these by eye. Okay, let's try and tack down the other corner here, shall we? If we can get in there. There we go. I think we've tacked down the other pin. So that chip can't move anymore. It's secured in place, and we can solder the other pins. Even though my alignment's a bit off there, I may need to reflow that and just shift it slightly. So there we go. I'll just reflow that and just move the chip gently into place until those pins line up. Perfect. Now there's one thing I forgot to use here, and this was the flux pen. I probably should have, with these surface mount parts, these surface mount ICs like this, I probably should have just pasted on a bit of a layer of flux before I actually, onto all the pads before I soldered that chip into place. But I'm just going to apply some just after the fact here. I'm just going to wet that a little bit on there, so to help the solder take to that when I drag it right across with my well-based tip. And there you can actually see the residue, the flux residue all around there like that. I sort of overdid it a bit there, but you can actually see it's in place. Too bad it's not actually under the pins, but it could actually flow back under, and that will be good enough, should be good enough. Okay, here we go. Let's feed some solder into the well here until we've got just enough to sort of make it sort of just swell out the bottom, and let's see if we can do this. Bingo, look at that, magic. And there you go, that's almost a near perfect solder joint on each and every one of those pins, and all I did was drag the soldering iron across. I actually dragged it across a couple of times because I didn't get it first go. It's a bit hard under the camera, and I haven't practiced today, which is something that you should do before you start out on an important board. Just even, no matter how experienced you are, just do a little practice run. Now, as you can see, we do have a tiny little bit, 2 pins shorted together there, but we can get our trusty solder wick. This is the really thick stuff. This is where the super fine stuff would come in, and we'll just wick that away. Bingo, gone. And we have a perfectly soldered 0.65mm pin pitch. And I don't know if you heard that on the camera, but there was a lot of sizzle there as well as the flux burnt, and the flux is really the key to doing this. I'll try and do exactly the same thing on the other side, okay, but I won't use any flux, and let's see what happens. Now that one turned out okay. There's one little solder bridge there, which I can fix up with either the solder wick, or I can just come back in with my wicking tip, okay, and just that will just suck that, if I can get in there, suck that away like that. Now that turned out all right, but it took a few swipes. It didn't seem as clean to me because the other side that had the flux on it just seemed to reflow much better. I just much preferred that. So the flux can be really handy unless you've got like a brand spanking new board, fully cleaned, you've got a brand spanking new component, and you know, no oxidization, then you can do without the flux, but the flux really helps. But there you go. That's how you can solder a 0.65mm pin pitch. You'd have a hard time doing those individually with each pin. You'd probably have to do it under a microscope to get a good result. But with one of these well-based tips, these things that actually have the well in them that wick the solder away, these wicking tips, they're great. Now what we're going to have a go at is soldering this PIC 24FJ. Not that it matters, it could be any chip, but it's a PIC 24F 0.5mm pitch quad flat pack. Let's see how we go. First thing we're going to do is just put some flux on these pads. Now you can use a liquid based flux if you want, and really, because we've got the gold flash pads here, you don't necessarily have to use flux like this, but I'm going to anyway, because flux is always a good thing. Trust me, it's the key to good surface mount soldering like this. And we're going to use our tack and reflow method here, so I'm just going to put a little bit of solder on that second pin there, because I didn't have to worry about getting it on the first one there, and we're going to tack that component in place in at least 2 corners. And we'll just reflow that pin there. There we go. And we'll just tack solder a second pin there. We can clean that up later. It doesn't matter if we've got a short there. And just to be sure, we'll add some more flux along there, because you can never have too much. Now the technique we've been using here is called drag soldering. As you've seen, we drag the soldering iron over the pins, and I've showed you it with a well-based tip, but you don't have to have a well-based tip. You can have a standard chisel like we've been using. Now, in fact, some people say it's better to use a chisel, but well, I don't know. Take your pick, really. But we can do drag-based soldering with a regular chisel tip as well. Let's give it a go. Here we go. We've got a 0.5mm pin pitch part. This is quite a very small part, pretty much as small as they get. So we've got some solder on the back side of that. Let's give it a go. There we go. It's not necessarily the cleanest result there, because there's probably a bit too much solder got on the pins, but we can actually clean that up. You can actually drag the iron back out like that and get the solder off those pins, no problems at all. But look at that. We've soldered, easily soldered, a 0.5mm pin pitch part. And granted, it's really easy if you've got these larger, longer pads that you can actually get the iron onto. So if you're laying out your board like this for these 0.5mm quad flat packs, it doesn't matter what size. This can be a big 200 or 300 pin quad flat pack, and you'll solder it just as easily and just as quickly. And to finish off this chip, you would just do exactly the same thing on all 4 sides, and clean it up with a little bit of solder wick if you have to, or as I showed, just dragging the iron back away from the pins. Now this one really helps because it's got really long, it's a prototype board, so it's got really long pads like this, and I don't recommend you, when you're laying out footprints, to make them this long, but something like these pads over here would be a really nice size exposed pad there, so that you can get your chisel tip iron, or the solder, the molten solder, the ball of solder, either in your well or on your chisel tip, so that it actually makes decent contact, thermal contact with the pad itself as well as the pin, and then with the flux it all just flows beautifully. And it all has to do with this surface tension of the solder, because some people look at this and they think it's just amazing how you can solder a 0.5mm pin pitch part with a couple of millimeter diameter chisel tip like this. You would think it's impossible. Well, it's not. It's because of the surface tension of the solder. It just wants to stay on the iron, or stay in the well tip or the chisel tip, and it doesn't, as we showed, it doesn't want to stick to the solder mask, the red solder mask material which is between the pads, and it wants to actually just reflow onto the pads itself with the flux there to help clean it. So really it is almost like magic, and there's no trick to it at all. It really is that easy. And if you don't feel comfortable actually dragging your iron all the way along these pins, especially the very large packages, you don't have to actually drag it along. You can actually just drag the individual pins backwards, as we saw like this. You can actually just get them like that and just touch it in like that. If that's another technique you can use. It's not as quick and efficient, but you can actually say that it is a bit it's a bit more precise than the technique of dragging them actually across the chip like that. So you can drag back. It might take you a little bit more, but you can actually get a bit more a bit more precise feel. And there you go, just that simple application of the iron, we have pretty much perfectly soldered one side of that quad flat back. And as with any solder joint, each one has to be a really nice shiny joint with a really nice fillet. It's really hard to get. Sorry, I can't actually zoom any closer like this under the camera, but you can see that really that only took me a couple of seconds, and each joint is pretty much almost perfectly formed. And as I mentioned in the first part of the tutorial, my soldering iron there is set to about 350 degrees. You certainly wouldn't want any higher than that. Anywhere from 300 to 350 is really going to do the trick for fine surface mount work like this, because if you make it too hot, you can actually lift the pads. You have to be careful, and especially if you apply too much pressure. If with your iron, if you come across here and actually apply a lot of pressure as you're sweeping across like that, you can actually lift the pad. So just be careful that you apply very light pressure, and in the case of the base tip, you really shouldn't even need to touch it. As long as the molten ball of solder actually makes thermal contact with the pin and the pad, it's going to reflow. So really you shouldn't be having any pressure at all on there. If you are, just very, very light. There's another technique that some people like to use, and you can actually use solder paste. This is just some basic solder paste with a little in a syringe like this, and you can actually just apply a small amount of solder paste either before you lay the chip down, or you can even do it after, which I'll show an example of here. But you really have to get just the right amount of paste on there, otherwise you end up with too much and then you've got to clean it off. But anyway, let's give it a go. Let's see if we can apply a small amount of paste across here. It's got it's quite hard under the camera here, but anyway, let's give that a go and see what happens. And you can likely hear that I've got my hot air gun here, once again set to about 350 degrees, and with a reasonable airflow on there. And let's heat up this and see if we can do it. Normally I'd get this right down vertical, but I can't do that with the camera in the way, unfortunately. Go on this, but it should. There we go. There we go. It's finally reflowing. Bingo. And that's not a bad result. I'd say I've used slightly too much solder paste there. As you can see, it's actually quite hard to dispense the correct amount of paste, and of course this is where you get into solder stencils and proper reflow soldering with a thermal oven, which won't be in this tutorial because this is about hand soldering. It's not about doing a solder paste stencil. But there you go. You can actually use a syringe based paste, and once again you can go along with your iron or your wick later and you can actually clean up that. Generally you're usually going to end up with more solder than not. Generally it's hard to put a very tiny amount on there unless you've got a specific paste dispenser. You can get automated pump based dispensers. They only dispense a certain amount of paste, and you can go along and actually apply it to each pad. You can go along and go bang, 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 bang on each pad like a little drop just before you place the chip down. But geez, if you're going to do that, well, you probably may as well do the stencil as well. But there are some cases where you actually want to rework boards with components all around where you can't actually get in there and do a solder, or it's not as easy to use one of those solder paste stencils. So you may have to use one of those pump solder paste based dispensers to just dispense the correct amount of paste on each pad. And you can actually get machines to do that as well, and I've got another video which I'll link to here, which actually shows you a very expensive high-end machine that can actually dispense paste onto individual pads in a fully automated type process, and that's good for reworking BGA components and things like that. Now you'll notice that I've been using a gold plated or a gold flashed prototyping board here. Now if you're going to do really high density fine surface mount work, I highly recommend that you get your boards manufactured with these gold flashed pads, because it is just, it's easier to solder to, everything takes better, the flux takes, you don't have to use as much flux, it's just nicer, it doesn't corrode as much, and it's just, and the other thing is that it is a much flatter surface, and that's quite important when you get down to quite fine pin pitches. You can get finer stuff than this, and if you get BGAs, it's actually quite important that you that the chip actually sits on all the pads quite flat. Now, if you compare that with a what's called a hot air level solder finished board, here's a typical one. It's not the gold flash. It's just a solder, a tin plate solder finish on the pads here, and you probably can't see it under the camera there, but the finish is it is lumpier, and the chip doesn't sit as flush as flat to the board. And if you've got like a BGA or something like that with the little balls in there, if you just get one pad that's got a bit of excess solder on it, then you're going to get a horrible result. So really, it doesn't cost all that much more. You know, it might even cost a few cents per board, really, to get the gold flash pads. I highly recommend it. Now let's try and solder on this a higher thermal capacity D-pack here. The others have been really easy because our soldering iron hasn't sweated the smaller stuff at all. But as you can see, this rather large device has a huge pad on the bottom and a matching pad here, which is connected to well, it's a reasonably large little heatsink here, as sort of a heatsink ground plane. So let's solder that in place and see if we can do that at the same soldering temperature we used before, 350 degrees C, with the same chip, our chisel tip we used before, and see how we go on that, see how long it takes to solder something of this thermal capacity. And of course we're going to have to tack this in place as well, so we'll just put a bit of solder on that pad there, and we'll just bring our device in and we'll reflow that in place. No problems. Do the other pad now. As you can see, we don't actually have any pad area there to actually apply our solder to, our iron to. So we really have to put the iron on top of the leg, apply pressure, and feed in solder from the bottom like that, and it reflows onto the pad and then onto the leg as well. Now I'm going to use my standard chisel, medium-sized chisel tip here. I've still got my iron set to 350 degrees as we've been using up until now, but I've got this large amount of copper. Let's see how it goes. Now, one method to actually do larger devices like this, and this is actually quite a small device, a D-pack. You know, if you've got a large TO220 and you're trying to solder to the tab or something like that, you may actually want to preheat it. What's called a preheating process, where you would, that's where your hot air gun might come in handy. You would actually heat up all of the surrounding copper in the pad and the component first, and then you can get in there with your solder and require less time. But anyway, let's not discuss that today. Let's actually get our iron in there, try and get it on the pad and the device as well at the same time, and let's try and get our solder in there. Now at the moment, you know, we're trying to apply it to the pad, and that's really not working that well. This is where, okay, we're going to have to put some solder onto our tip like that, so that we can actually better thermally couple onto both the pad and the device. So we've now got solder on there, and you can see it already starting to flow onto the pad, and there we go, bang, it's starting to flow along, and it's starting to heat up both. But as you can see, it's taking a bit of effort. You can actually see parts of it cool while the others actually heating up and is molten. The other end of it just instantly cools and solidifies. Look at that. But there you go. We've actually now completed that. But this isn't ideal because it's only
actually attached to the top. We haven't actually reflowed any under the bottom. This is where some thermal paste would come in handy, to actually put some paste on the bottom of that device, and then you would actually reflow that with your hot air gun on top. But anyway, that's okay for just a simple prototype. But of course, I'm not entirely happy with that. Look, it's all lumpy, and it doesn't, it's all craggy. I don't like it. It's not as shiny as it should be. So let's get our iron back on there, shall we? We try and get this one flat to apply a much more even heat. So we'll leave it there for 5 seconds or so, and we can heat up both the pad and the device. And this is where we might want to turn our temperature up a tad. But as you can see, we're already starting to get a much better wetting between both surfaces there, and we've probably got a little bit too much solder there actually, so it's not going to look perfect, but that is better than what we had before. And there you go, that is quite a nice, shiny, smooth result there. And that device is still hot. It's still very hot after the process, but these larger components can actually take more of the heat like this, and they will actually trap the heat for longer. So just be careful not to touch them, because after you've soldered them, because they will still be hot, retaining that heat as part of their thermal capacity. That's their job. Now with these small components like this, these passive components, they can be quite easily damaged by excess heat. You have to be very careful with them because there's no thermal capacity in there at all. So most of the temperature of your iron is going to go straight into that component very quickly. Multi-layer ceramic capacitors are one example of components that can be really damaged very easily with excess heat. So you want to be very quick, and you want to use as lower temperature as you can get away with these devices. Otherwise you can lift the end caps off them, and your boards as well. Your FR4 PCB material, you can get different temperature grades which will handle heat better than some will handle heat better than others. But if you've got a poor quality FR4 material that uses poor quality glue and resins and things like that to actually stick the copper down to the FR4 material, then really these pads can actually lift straight off the board if you have excess heat or leave it there for too long. So just be aware of that. Let's actually see if we can do that. I've turned the soldering iron up to 450 degrees Celsius, and I'm going to heat up this pad here. Now it could take a little bit, and especially it does it a lot when you're doing rework and stuff like that, if you have to rework several devices. But there we go, bingo, it's gone. There we go, we've lifted, check it out, we've totally lifted that pin up. It's buggered, look at it. See? It's just totally floating and hanging on to the trace like that. Thank goodness that the copper actually still hangs on there. So you can actually, if you're very careful, you can actually push those back into place. If you do lift them, can push it back into place and then still solder your IC on top. But you've got to be careful of that. That's what can happen with too high a temperature.
I told you it was easy. Look at that, 0.5mm pin pitch parts. Why be scared of it? You can do it in a couple of seconds with just very basic tools and hardly any experience at all. It's unbelievably simple. Now, we didn't cover solder stenciling, which is a different technique, and put it in the reflow oven and things like that. Maybe we'll cover that sometime in the future, but this is just hand soldering, and you need good hand soldering skills, even if you're going to stencil and reflow your own boards, because sooner or later you're going to have to rework parts, and rework soldering techniques are slightly different as well, especially removing parts. Maybe we'll do another tutorial on just reworking parts, but hand soldering skills, very important, and there's no need to be scared of any components like this. Surface mount components are easy to do. Basic chisel tip soldering iron, some fine solder, a well-designed board with well-designed pads, and the solder mask. Make sure you get the solder mask between the pins when you're laying out the board. Watch for solder mask expansion. go Google that. I think I've probably done that in a previous tutorial. Solder mask expansion is important to get that right. But if you get those things right, you can solder all these boards yourself at home very quickly, very professionally. Simple, basic tools. So there you go. I hope you learned something, and go out there. Don't be afraid of surface mount parts. They're a piece of cake. See you next time. And don't forget your flux. Flux is everything.